Hello everyone. Today we are diving into a banking concept. To begin, I will explain the fundamental problems that makes banking necessary. We will start by looking at the core challenge of memory management and specific issues called external fragmentation. In a simple word, when we run a program, the operating system finds a big empty space in the computer's memory or the RAM and puts the whole program there. As you see here, process A, B, and C are loaded into nice, neat, and continuous blocks. At this point, everything is efficient. However, a problem starts when a process is closed. Let's say process B finished its task. The operation system frees up its memory, but this creates a hole and empty space stuck between process A and process C. This space is free, but it's fragmented. This brings us to the core problem, known as external fragmentation. Now a new program process D needs to run. If we add up all the free memory, we might have enough space for it. But because that free space is in one solid block, there is no single place large enough to fit process D. This is the definition of external fragmentation. Memory is wasted because it's broken into small, unusable pieces. This is the specific problem that Hagen was invented to solve.
Paging is non-contiguous memory allocation technique. It's one of two memory allocation techniques, which is paging and segmentation. It is used by operating systems to manage memory more efficiently. Instead of allocating one large block of continuous memory, paging divides the logical memory into fixed size blocks called pages. The same thing happens with physical memory, which is the RAM, and is divided into blocks of the same size called frames. When you load a program, its pages are stored in any available frame inside the RAM, as well known as the physical memory, regardless of where it is inside. This helps the main problem, external fragmentation, because the pages don't need to be stored next to each other, which is non-contiguous. In a paging system, the logical memory, which is the memory seen by the process, is divided into fixed size blocks called pages. At the same time, the physical memory, RAM, is divided into the blocks of the same size, and these blocks are called frames. When a program is running, its pages don't need to be stored in a single continuous space. Instead, a page can be placed into any available frame in RAM. But since the pages are scattered, the operating system needs a way to find or a way to keep track of where each one is. That's where the page table comes in. It's a data structure that helps each page number to the frame number, where that page is stored. So whenever the CPU needs to access data, it uses the page table instead to find out which frame the required page is inside, and then gets the exact physical address. So how does paging fix external fragmentation? Let's assume that we have a job containing 350 lines. The physical memory may have enough space to contain 350 lines, but they are scattered due to external fragmentation. So it might have 100, 50, 35, and so on and so forth. So the process then is segmented into pages. So 100 lines, 100 lines, 100 lines, and 50, instead of just 350 lines back to back. Each page is placed into the frame inside the physical RAM, and then the page table helps find that frame by providing the corresponding date or corresponding number. The advantages of paging and disadvantages include: for the advantages, it avoids external fragmentation, which is our main issue. It has efficient memory use, since it's using as much memory as it can, no matter how much the size is, and allows job allocation in non-contiguous memories. So it allows job allocation inside of a memory that isn't connected together, so the edges aren't connected to end to end. Some of the disadvantages are internal fragmentation in the last page. So for example, let's consider a program as well, 350 lines. The last 50 lines may take 50 out of 300 empty spaces. So it means there's internal fragmentation in there. And higher overhead compared to systems with direct memory mapping. That because paging has so many translation stuff from logical address to physical address and so on, this may affect performance, making it slower and so on.
Alright, now that we know what paging is, let's talk about how it's translated. When a program runs, it doesn't know where its data is actually stored in physical RAM. It sees a clean, logical view of memory, but the OS and the hardware know the reality. Memory is shared, scattered, and limited. This is where the Memory Management Unit, or the MMU, comes in. It takes each logical address that the CPU creates and translates it into a physical address using something called the page table that is located within it. Let's see how this works step by step. Every logical address consists of two parts, the page number and the offset. The MMU uses the page number to look up the page table, which tells it which frame number in RAM holds that page. It then combines the frame number with the offset to create the final physical address where the data lives. To speed things up, the MMU uses a cache called the Translation Look-Aside Buffer, or TLB. If the page number is already in the TLB, which happens often for frequently used data, we have a TLB hit. This means we skip the page table lookup completely. It's like already having the answer ready, so translation is much faster. But sometimes the page number isn't in the TLB. This is called the TLB miss. Now the MMU has to look it up in the page table, which takes longer. Once the frame number is found, it still completes the translation like before, just a bit slower. After that, the TLB is updated so future lookups can be faster again.
Now that we've seen how paging works, let's talk about one of the main problems that can happen, the page fault. A page fault occurs when a program tries to access a page that is not currently loaded into the main memory. This means the system needs to pause the program, fetch the required page from the disk, and load it into the RAM. Once the page is loaded, the page table is updated, and the process can resume execution. On the right, you can see a simple flowchart showing this process, from detecting the page fault to resuming the program. This mechanism, allowing, uh, this mechanism allows paging to work flexibly, but as we'll see in the next slide, it comes with performance cost. So, what's the big deal about page faults? Well, they're slow. Accessing the hard disk or even SSD is much slower than accessing RAM. When page faults happen frequently, it can seriously degrade the system performance. In severe cases, the system may spend more time swapping pages in and out of memory than actually running processes. This condition is called thrashing. To reduce page faults, systems use techniques like better page replacement algorithms, increasing physical memory, or using TLBs to speed up address translation. Let's quickly summarize what we've covered with paging. On the positive side, paging helps eliminate external fragmentation, uses fixed-size blocks for easier memory management, and allows efficient swapping. But it's not perfect. Paging introduces some overhead. Maintaining a page table takes extra memory, and TLB misses can slow things down. Worst of all, page faults can interrupt program execution and hurt the performance. So, while paging solves one big problem, it introduces new challenges that need to be managed carefully.